Welcome to the hydroponics revolution, where efficiency, emerging technologies, and scalable growth intersect to reimagine farming. This cover image hints at soil-free systems that use precise nutrient delivery and compact vertical layouts to produce more with less water and space, setting the stage for how sustainable, high-yield food production can meet rising demand in cities and beyond. The nutrient film technique, or NFT, works by circulating a thin film of nutrient solution, so roots get steady access to water, oxygen, and minerals while remaining easy to inspect. This slide shows how continuous flow prevents salt buildup and nutrient lockout, reduces media costs, and fits neatly into vertical racks, making it ideal for leafy greens, herbs, and high-density cultivation. This timeline traces hydroponics from ancient terraced gardens to modern high-tech greenhouses, highlighting key milestones like nutrient research in the 1860s, practical gravel and sand systems in the 1930s, and large-scale validation during World War II and by space programs. The story shows how centuries of experimentation and scientific advances paved the way for today's scalable, sustainable soilless agriculture. Deep water culture suspends plants on rafts above an aerated nutrient reservoir, so roots stay submerged but oxygenated via air stones. It's forgiving with pH swings and simple to run for hobbyists in buckets. Yet commercial DWC integrates DU sensors, chillers, and climate controls to optimize root zone conditions for high biomass crops and continuous production. Ebb and flood systems periodically flood and drain media beds to oxygenate roots through intermittent exposure to air, while drip systems deliver calibrated solution directly to each pot for precise feeding. The slide contrasts the oxygenation and simplicity of ebb and flood with the dosing flexibility of drip systems, which are especially suited to fruiting vines and integration with organic fertilizers or beneficial microbes. Healthy hydroponic growth depends on a balance of 14 macro and micronutrients, with N, P, and K driving vegetative and reproductive stages. The slide highlights formulation choices like chelated iron and calcium nitrate for solubility and efficient uptake, and explains that tuned nutrient ratios prevent antagonistic uptake, so plants achieve vigorous vegetative growth and fruitful yields in later phases. Optimizing pH and electrical conductivity is central to nutrient availability. Keep pH between about 5.5 and 6.5 to avoid locking out elements like iron and calcium, and maintain EC roughly 1.2 to 2.0 ms/cm1 to signal ion strength. These measures guide dilution or replenishment decisions, help avoid osmotic stress, and ensure steady, predictable growth rates across crop cycles. In sealed greenhouse systems, precision environmental control boosts leafy crop yields while saving energy. Tune LEDs to 450 and 660 nanometers and target about 17 molem to day 1 DLI for leafy greens. Cut energy versus HPS by roughly 40% and maintain 18 to 24 degrees with 50 to 70% relative humidity. CO2 enrichment around 800 ppm can further accelerate photosynthesis in a sealed, recirculating environment. An intelligent nutrient management system streams pH, EC, dissolved oxygen, and temperature to a cloud dashboard for real-time monitoring, while machine learning models analyze trends and predict consumption curves. Automated peristaltic pumps dose nutrients and smartphone alerts warn of pre-deficiency, reducing fertilizer use by about 25%, while keeping crop quality consistent and enabling data-driven operational decisions. Closed-loop water recycling and vertical stacking maximize water and land efficiency, recapturing transpired vapor and filtering recirculated solution to reach about 95% water use efficiency, compared with roughly 20% in soil. Stacked vertical towers dramatically increase yield per hectare, spare arable land, and eliminate agricultural runoff that would otherwise threaten freshwater ecosystems and downstream communities. This slide compares traditional energy demands with renewable-powered greenhouse options and highlights supply chain benefits. By integrating solar or wind and efficient systems, greenhouses can lower CO2 per kilogram of lettuce versus field production, while local, year-round production shortens transport, reduces spoilage, and strengthens urban food security through more resilient, shortened supply chains. Advanced hydroponic technologies combine AI-guided breeding, quantum dot LEDs, nano-bubble oxygenation, and integration with aquaponics and renewable microgrids to unlock higher yields and efficiency. These synergies can push toward net zero operations and resilient food systems, positioning soilless agriculture as a cornerstone for sustainable, high-output food production in the face of climate and resource constraints.